Hello, welcome to my open source tech conference talk about our war story using Mainline Linux from Android TV BSP. So first of all, I am Neil Armstrong. I work for Bailey. We are a small engineering company located in south of France, near Villeneuve, and I'm a kernel developer. I was pushing upstream Linux for the last 4 years and working for the embedded Linux field for the last 12 years. So first of all, the timeline of the talk will be first we'll speak about Android and the relationship with Mainline Linux. A little bit of history about the Android Hardware Abstraction Libraries. How GPU are integrated, the different boot flows to boot Android, the other integration issues we encountered, and a conclusion. So the scope of the project we worked on was to build an upstream AOSP BSP for the brand new AMG SoC that were disclosed last year. So the target was the Android TV profile because now it's available in AOSP, and the initial kernel version was 4.19, and on 4.19 the new SoCs were not supported at the time at all. The team had small but still AOSP BSP porting experience, but it was old. About the time the first telephones were designed by Google, like for Android 1.6. So Android and Mainline Linux. So from the beginning, the relationship with Mainline Linux is complex because historically, when Android was developed at the time, Linux was not multimedia ready at all for ARM ports. So they needed a lot of multimedia support for the GPU, for the camera, for power management, and so on. So none of this was available for ARM devices. Everything was for Intel and maybe PowerPC, but not for ARM. So hopefully the vendors had the support in their trees, but like every vendor support, it was different for every vendor. So different for TI, different for Samsung, and so on. So recently, the last 2 years, Google outlined multiple efforts to solve this issue. This is a long remaining issue. So the first one is Project Rebel. We know as GTI today. It's a list of kernel ABI. So for each LTS kernel, they listed all the kernel ABI, the functions you can use from modules, and they defined it as an acceptable vendor interface, stable vendor interface, in order to have a generic system image. So you can have a single image, and each board support for the phone, for example, or the phone features will be developed as modules, and the module we will use only these particular symbols. And the last effort is one kernel to put them all. So the goal is to have a single build, so a single kernel build, and so all phones will ship the same kernel, but each phone will have some different modules. So if these modules were developed using the GTI treble kernel interface, they will be accepted and used along this single kernel build. For Mainline, AOSP 10 now can run Purvania because when Android was introduced, Google introduced some subsystems, for example, for logging, for power management, and they were not completely acceptable to be pushed upstream initially. The logging module did come, but all the kernel code for power management was not acceptable. It was too complex and too deeply integrated for Android. So it took a long time, like more than 10 years, to have it finally integrated, an alternative. So Google now use these drivers, and using Purvania with some specific configs, you can run AOSP 10 with Vania kernel. But it's still needed to have to use an Android derived branch because they have a set of kernel config. They have scripting to generate this config. They have their own fix and patches for performance, for example, to fix some corner cases. And they have their own build system for the kernel integrated with Celang and YAML and all the tools centralized. All this to be done by a build server, to be automated. So our use case, concerning Mainline Linux, it was no vendor kernel at all, only Mainline. This means to support these two new SoCs, so the S95X2, the S95X3. We need to develop support for these SoCs. Push the support upstream. So at the time we started to push on 4.2021 and backport all the patches for 4.19. So what is the process? So it's a usual process we do. It's our job in Believe. The process is simple. You push to the main list. You rework until the maintainer are happy. The maintainer takes the patches in their tree. Their tree is merged in the master tree from Interval. Interval tags a release, and then we can get all the patches that were merged and backport them on the Android tree. There are some rules that was introduced by the Chrome OS kernel guys to distinguish between the original commits from Mainline Linux and from backported ones. So you have the upstream tag, you prepend on the commit message, which means it's a pure commit that was cherry-picked and backport without any change. So backport means it was fixed to apply or to build, and the from list means you took the patch on the main list before it was accepted by the maintainer, because it's possible to do that if the patches is complex, too complex to do in a single pass, or the time frame is too short. So this is a description of the flow to develop. So we work in our integration tree in top. We push on the main list, so the correct main list for the correct maintainer with the correct reviewer. So it's merged on the kernel.org master branch. The stable tree is taken for the master branch. The Android trees are synchronized with the stable trees, but in blue you can see that we backport directly the new patches on the correct project tree, which is named Yukawa. So the final goal at the end of the cycle, you see, is a web base. The goal is for each LTS to support the same features, without spending 1 year to develop all the features or to fix to the features. So with this system, if we backport everything, when we rebase, Git will automatically remove all the commits. So the rebase will be simple. You only will remain the from list is the Android specific patches on the new, for example, 5.4.3. So why upstream first? It's a good question, actually, because we could develop everything in a tree and use it and rework everything for the next kernel. But the great advantages are easy maintenance with upstream first, very fast rebase, like we saw, to drop all the backports, and we simply show the new sort out the non-upstream patches. So you will only need to concentrate on the non-upstream patches or the from list. For example, text new ones, simply. And it ensures very good quality because in order to be accepted on upstream kernel, you need to have a very good quality. Maintainers are very picky because they will need to maintain these patches, and maybe yourself, because we maintain some of these subsystems and patches and drivers. So we need to have a good quality and a good code organization to make sure it's easy for us to maintain everything. The code is slower because you need to make more complex and more not complex. The architecture of the driver are not different between an upstream driver and a kernel driver. You need to make sure it match everything to be upstream, so it's more slower. And the main issue is when you need to add complex feature that will result in a hack, for example, in a upstream kernel, like very complex multimedia features like HDCP, video decoding, and so on. You will implement it very easily, or take the vendor patches and apply them. But for upstream, it's much more complex because you need to make sure it doesn't break other drivers. It fits in the framework. It's clean, future-proof, etc. So this is a complex part of the project. So this is why the from list exists, because for very complex patches that can take multiple years to go through, you can take the intermediate work that has been posted and say, oh, later I will take the new work I did with a small change, the small rework, and backport them later on. So you still have non-upstreamable patches, really Android-specific features, or this because honestly, when you do a product, you always have corner cases that cannot be solved by something clean or easy. Or so, like every project, you need to have project-specific patches. So there is another tag called Android, or for the name of project like Yukawa for us, that is acceptable. But if you want to have a easy rebase and an easy maintenance flow, you need to limit this to really a few patches for a project, for a product. So the big subject about Android today and the original is the hardware abstraction layers. So Android is really based on frameworks, which are the features accessible by Java and Kotlin, and the hardware abstraction layers. It's really the translation of the framework features into system calls that we speak to the drivers. So why was it cut like that? Because it's really generic. Because at the time, like I said, ARM Linux at the time was was very limited and was not really made for multimedia. So there were no dynamic graphic stack, for example, only the basic single plane frame buffer without any mode setting. No sensor framework at all. Very limited runtime power management. All the media, camera stuff was very limited. It was really oriented for PCs, so only capture for TV capture and so on. So this is the global architecture of Android, which is still the same today. It didn't really change at all, except behind this, the names of the blocks are maybe somehow different. But still, it heavily relies on hardware abstraction layers for camera, audio, graphics, and other system-related features. Maybe the difference today is now it can use mainline drivers. So at the time, there was a very limited managed support for multimedia. So they told the vendors, okay, you can take your tree with multimedia and power management features, but you write the abstraction layers for us to make work the display, GPU, camera, and so on. And we will put all the power management, syslog, and system management ourselves. So this is why until very recently, every vendor wrote their own hardware composer display module, for example. You have a specific graphical allocation module for each GPU vendor today, still today. There is no generic one. So for the Google part, it took a very long time until AOSP could run vanilla, because the kernel developers took very long time to push a serious alternative. I mean serious, that could run on the device. But for the kernel developers, they wanted to have alternatives that could really run on all platforms, not only ARM Android platforms. And Google took a long time to adopt the alternative. And for them, for multimedia, the DRM framework, the direct rendering manager with kernel mode setting took a long time to mature. But now, in the last 3 years, every ARM vendor took seriously this framework, and now give support for it. But there is still a lot of work. So what is our usage for hardware abstraction libraries? So hopefully we make use of default ones for now, because hardware composer generic HL was developed, which is DRM hardware composer. It was a use blocker, because without this, we will need to develop our own, which is a complex piece of code. All the Bluetooth, Wi-Fi is generic. So we only have the graphical module, because it's needed for the ARM binary Mali integration. For the HDMI CEC, but we could write a generic one, but it's not really used out of Android TV. And to control all the lights of the board, you need a custom one, but that's it. This is really a small piece of code, so it's not an issue. The GPU is a big subject. So how it is integrated. Here is a diagram of how all the GPU related features are integrated. So you have on top the Android framework that will use the graphical module to allocate all the media buffers. So the media buffers will be allocated in the kernel to match either to have to match the memory constraints. These Graloc allocated buffers will be passed to the OpenGL Vulkan library. The GPU will don't do this work. Okay. Then, if say it's a buffer with a rendering frame, it will go up to the hardware composer. If it's DRM, go to libDRM and go to the DRM display. And you have the similar stuff for the video decoding. So you will have allocating with Graloc, go to the codec module, speak to the decoder, and go back to be rendered either on OpenGL or on the display. So the relationship is really the GPU library, Graloc, and Hardware Composer. They developed their own OpenGL API, which is different from the Linux one, the Apple one, the Windows one. The key is the private handle T structure, which is the key relationship between the Graloc GPU library and Hardware Composer. This handle T is used by the GPU by Graloc to store all the attributes of the buffer. For example, the data buff, frame descriptor, the size, etc. It can be used by the GPU, not mandatory, but it can. Then it's used by the Hardware Composer module to import the buffer and push it for DRM, for display, or other ways. So how ARM Mali is handled like this. So ARM provides an open source Graloc module, which is great. But you need to use the correct Graloc module, the same version as the OpenGL library version. ARM changed this private handle T often. In each Graloc N DDK Mali, they change the content of the structure. So it's complex. So if your vendor, like Logic for us, provides the OpenGL library, you need to use the same version. And for example, Logic modified this structure for their own needs. So we need to use the same structure. So we are tied to use the same Graloc module, which is weird. And if you need since you need custom module, custom structure, you need to have a specific vendor implementation in Hardware Composer, which is another complexity, but it's okay. But Hardware Composer, it's an external generic shell. It's developed on free desktop, which is great because they take easily merge requests, and you can have new platforms easily. So upstream-first here also. There's still a lot of issues. For example, the Android graphic stack doesn't make any difference between the actual UI plane size and the display size. So, for example, a lot of Android TV low-cost hardware, like the Logic ones or Luminar chip, has a very limited bandwidth for the UI layer. So on all the SoC, they want to keep the Android UI in 1080p. But there is no way to say to Android, okay, we will take the graphic mode, the 4K display output mode. So the SoC will send 4K pixels for each frame, but we want to keep the UI 1080p. And we will scale it in hardware and everything is beautiful. But you need to lie to Android and say, oh, there's only a single 1080p mode. And do your own stuff in Terraform Composer to render in 4K, which is lame. So the boot flows. The boot flow in another subject, because booting Android is not easy at all. It doesn't follow any standards in any ARM or other platforms. They have their own standard, and until now, every vendor had their own standard. For example, Qualcomm packed multiple device tree in a single image and so on. So you have the old way, which consisted of a boot image plus an init.rd to load. The boot image contained the kernel and the device tree added at the end, because when the first device was developed for Android, there was no device tree, so they needed to use the same very old boot flow with device tree without changing the boot flow. So the system was mounted by the init.rd, then the vendor, and was booting Android. This boot flow is still compatible with Android 9, not Android 10. The new way that was introduced is system as root. The kernel, there is a kernel with DT now in the second payload, which is not catted to the image, and eventual DTPO, which is a DT overlay. It doesn't have an init.rd, but there is some patches in the kernel that allows the kernel to mount the system as a root of the system directly using UID. The vendor is defined, the vendor partition is defined DT, and you mount it. That it was introduced for Android 9 and mandatory for Android 10, if not using the new way v2, which is a dynamic partition. The dynamic partition means there is instead to have the system plus user data and so on. There is now a super partition, which is a big partition. This is dynamically cut in different partitions. So you still have the kernel boot image, and they reintroduce the init.rd. That yes is used to cut the super partition into different bits. So now, like before, the init.rd boot mount the system and vendor and all the partitions from the super partition, and is mandatory for Android 10 if you don't use system as root. So it's complex because all these boot flows are really complex, completely different. It's hard to support because they introduced a lot of stuff that is not compatible with older Android. So the simplest is support Android 10 with system as root. We still support the new video features in U-boot, but hopefully Google TI and other vendors push support for all the Android boot flow into U-boot and Mainline, which is great because we can we're able to script all the complex Android AB and so on boot flow in U-boot, which is in the Mainline U-boot, which is cool. So all the reference board of the Yukawa project we developed are supported in Mainline U-boot, which is great. But we still need like other projects, a few hacks that are complex to integrate in U-boot, but it will be solved over time. So what are other integration issues we encountered? Audio. Audio is a mess because when I did a port for Android 1.6, it was already a mess. You need to write your own ALSA module, and it's still true today. Google doesn't give nothing for audio. Now we have a very complex and powerful kernel ALSA SoC framework. So I would think, I would assume Android, Google has developed a complete framework to handle that, but no. You still need to develop your own one for each SoC, for each project. So the solution was to use the old tiny HAL from Cirrus Logic, was that is here for like 10 years, and adapt it for your own needs, which is a pity. Wi-Fi, it's a complete mess. They use old WPS Beacon Fort. They tweaked to communicate with it. It's a complete mess, but seems they are moving forward and developing a complete and clean Wi-Fi module like they did on Bluetooth. But Bluetooth was not a mess because BlueZ was already a good thing, but they avoid everything, so they will do it for Wi-Fi, which is a good point, because they add some vendor-specific modules for each Wi-Fi vendor, which is stupid because the kernel introduced a generic Wi-Fi API, so we don't need any more of a per vendor user space implementation. But all this is legacy. Hopefully, it's moving forward. Display mode, which is, like I said before, an issue with the graphic stack on Android. When you deal with all the HDMI to 4K and very complex, you can have multiple display modes with the same width, height, and frequency, but that are slightly different. Some has different encoding and so on, but you can't give to Android the difference between these display modes. For them, they take only these three properties for a mode, which is stupid because when you support the full monitor, you can have like 15 or 20 modes, and some are duplicated for good reason because they are slightly different. Some has DVI, some are HDMI, some has audio or not. So, and you absolutely can't say to Android, take this one and not that one. So, for example, there is no interlaced support. You cannot. There is no flag to say, "Oh, this mode is interlaced." So there is not handled at all. So you cannot make the difference because between 1080 E interlaced and 1080p non-interlaced. And we struggle also for all the hardware decoding, video hardware decoding. So it's not on the slide, but Google are completely reworking all the codec stuff. They're going out of stage fright and developed a codecs called Codec 2, where they are trying to port the Chromium V4L2 memory-to-memory hardware decoder code, but it's complex. It doesn't work. It's a mess because Android you can allocate through Gralog, through Ion, and backport, and you need to go through 10 modules to allocate a buffer and come back. And it's a mess to develop and to debug. So it's not working. It's not open source yet. And it's the only point that is not working on Android TV BSP. So you cannot play video, which is a lame because we support and we push upstream the hardware decoder support for H.264 and PEG2 and VP9 4K, and we cannot make it work in Android, which is sad. So conclusion. So you can find all the code of our Android BSP. It's named Yukawa, and is the BSP for the iMusic new SoCs. So hopefully it's great news. Android is much more mainline friendly than before, which is very great. Common and modern kernel API are now supported. which is nicer than before. We still have a very long road because before having a single kernel that is really shipped on multiple phones and multiple actual products is still a project. It's still a long road before you have a phone with mainline vanilla kernel with a few patches. Because, for example, Qualcomm is very slow to push support for the new SoC. So it will come, hopefully. For the GPU nightmare, hopefully Panfrost, the open source upstream support for the Mali GPU, will maybe solve the nightmare, and we won't rely anymore on the vendor Graloc and binary libraries. And still there is a lot of work for other composer for real life display drivers. So thank you for listening, and this is the end of my talk, and I'm waiting for your questions on the platform. Bye.